So this is the second time I am coming here. The first time I came was when Ronojoy was around. Now, of course, he is settled in probably greener pastures. And it's also very nice to see a lot of old friends out here, especially from IISc, though, of course, they are all mostly younger to me. I think Pinaki and Samriddhi and Shaurajit, I did have encounters with them. There's some overlap with them at IISc. The one person, of course, is somewhat senior who was there when I was around, and this is the chair of today's session, Abhishek, and we used to call him Dabhi then because that was his email. And of course, he was known as a person who just worked and did things that I had no clue about. I am also doing things now on which I had absolutely no clue about when I was doing my PhD. And that is what I have the temerity to talk about those things. So please bear with me. This was never my focus area, but as days evolve and you evolve, you pick up things. And especially when you have nice students to teach you, I think one does make some progress. So this is what I'm going to talk about today, unraveling some method in these apparent madness of fluctuations that you have in the mesoscopic world of small particles. And the reason that these fascinate me completely is that finally life is made of these small fluctuating entities, which are of course living. And of course physicists, humanity has very, very little clue about how these things really work and how they themselves are living and walking around. And these billions of molecular motors which are always and continuously doing work fantastically efficiently. And we try to study them and we try to mimic them and perhaps understand how they are so good. So that is of course a long-term thing that we ought to have. And I come from IISc Kolkata, and the lab is called the Light Matter Lab. And these are the students who have developed what I'm going to talk to you about. And this is this guy. Two of them are here, Shubhajit and Vishwajit. So this guy is the person who really set this all up. Another person, of course, he's just next door, IIT Madras, Basudeb. He was the first graduate out of the lab, and he's now grown big and associate and all that, professor. He had just done a little bit of sort of the tip of the iceberg, but it was Shubhajit who took it on, and he then of course moved on to Germany, and now again he's back, and he's going to give a talk here on Saturday, and on the 20th, last day. And unfortunately, I'll not be there to egg him on, so I request all of you to hear what he has to say. Vishwajit has a poster outside. Anisha is the youngest, kid in the lab. She's just sort of starting about 1 year down. These two, Shubhra Kohli and Abhijit, are the ones who have all finished and they're off. And so Shubhra was actually the guy, both are in Germany, who started working on this non-equilibrium stuff. Shubhajit had set up stuff which was still more equilibrium dynamics. So now, just yesterday, I guess, one of the old friends, Shaurajit, so the image that I have in IISc is the guy who worked in Vasant's lab and was lasers doing these things with atoms and ions and trying to measure whatever frequency. That part, frequencies were not known, what I did. What was known was we worked in atoms and ions and tried to cool them. So lasers, this was called the laser lab, and I have an association with lasers, of course, and that image, of course, still sticks. So he asked me in Bengali, so that effect will not come, but when I reproduce this, what he said was, are you still with laser taser? So yes, I do work with lasers in optical tweezers, but there are a lot of tasers around, and very, very diverse things, which start right from very exotic properties of light that are revealed through optical tweezers, that is spin-orbit interaction, where light, angular momentum, spin angular and orbital angular momentum can basically couple and create some extremely exotic effects. This is something that we are very proud of. We have developed in our lab, by the way. So this was written by that technology we have, which it's a bubble which sort of moves. when I move my laser, and it also patterns as it moves. So any material that is there in the fluid actually self-assembles and forms permanent patterns. You see this is 2 microns, this is isowritten, and we call this microbubble lithography. And this, of course, has helped us in also creating some very nice non-equilibrium conditions in the lab, which we actually use to do this, statistical mechanics of mesosystems. This is again something very different. This is trapping of particles using photophoretic forces, which is not really optical dipole forces. And these create very stable traps, and these are actually, this work we have developed not using commercial microscopes, which I hope some of you at least are aware of, are typically used for optical tweezers. So this is a setup that we have entirely developed, and this is also a complete gold mine for non-equilibrium stuff, because it is trapping using heat and trapping very, very efficiently using heat and air. And in air, it's very, very difficult to trap things. By the way, so this is optical tweezers. So that is what the lab completely focuses on. Optical tweezers, we have now about 4 optical tweezers in the lab, out of which all of them are employed for different things. The last one is not really tweezers, but it is essentially we make these waveguides out of these biomimicking, mostly peptides and all, and they show some very fascinating properties in terms of light guiding and all that. So that is something which we have started about 3-4 years back. But of course, today's story is on this, and I like to tell stories, and what I will tell you is, of course, the journey that we have taken for the last about 6 or 7 years. And what I will stress upon are the experimental nuances, because I know people here, this is a focused conference on non-equilibrium dynamics, and I am not somebody who is in the theory. I have been doing it, last 5-6 years. So I know there are people here who are much better aware of the theory than myself. But in India, as is the tragedy, I may say, experiments are not something that we really are specializing in. And I think, with the exception of our lab, we probably have Rajesh and Pawan and Vijay at Pune. Very few people are really working with optical tweezers and in this domain experimental stuff. So I'm going to really tell you how difficult, not difficult, easy. I mean, what are the things that you do in experiments in order to make any measurements of these very tiny measurements of particles actually fluctuating, and most importantly, finding out generic patterns, because that is what is most important, because these are very small particles and their trajectories or the fluctuations are even smaller. So unless you can measure reliably, what you're going to get and what you're going to conclude is going to be disastrous. So that what you do in order to get to that is mostly what I'll focus on. And of course, incidentally, what we have done, the physics also would, of course, come out as a result of that. So this whole thing started when I think Basudev was looking at, 2 particles trapped in 2 optical traps and 2 optical tweezers, and trying to see if one moved, how would the other respond? In the sense, he was giving a sort of a square wave and looking at the displacement of the other particle and seeing that optical tweezers, of course, uses focused light to trap particles. That I'm not going to tell you in detail. If you're interested, a lot of stuff available, but essentially it uses optical gradient forces. Dipole forces, there are 2 things, gradient and scattering. Gradient forces help you to trap, scattering is destabilizing. But so you have a trap time constant, which is dominated by your trap stiffness, gamma by k. This gamma is the viscosity, k is the stiffness. So there is a time constant, and there is if you give a square wave, then that also has it has a rise and fall. So you will look at things, how the motion of the other one is getting affected. Shubhajit took it off. So by the way, besides, I'm just jumping a bit. So here, of course, is the wondrous world of mesoscopic particles, and why these are interesting is these actually do work. So you have a ratchet here, and you have this, these are birefringent particles, and these are rotating, and there's a flow, and these things go by, This is another particle which just goes around. So this is interesting, as I said, because this is how life works. This is, for example, sperm cell. This is a kinesin working, and then this is fluctuations, of course, that we actually measure. This is entropy, probability distribution. This is the work probability. Our contribution is that, you know, we have these bubbles which move, and you pump in heat. Therefore, it is non-equilibrium. It creates flows and flows of liquid. And if you have a particle trapped close to it, that particle feels a very, very interesting environment. However, coming back to the story, what we really wanted to look is at a coupled pendulum. Coupled pendulums are trivial, of course, if you're doing them in air because of the inertia. In an overdamped system, which is optical tweezers, they will not work because the mass is gone. The mass is damped out, right? However, there is still water that has a certain viscosity, of course, friction. So the question was that we wanted to ask was, what happens if I take this system in water? And how does it look like? This. You have this particle trapped, this particle is driven, and this is how it really looks like, this is schematically, cartoon. So we were doing this. Shubhajit, however, did not give a square wave, he gave a sine wave. And then in a lab meeting, he excitedly told me that he was changing, as he was changing the frequency of drive of this particle, this guy was responding differently, which was not expected. This was showing a resonance-like phenomena, which was not at all expected because this is a highly overdamped system. Only thing was we kept these very, very close. We kept this, so these are like 3 micron particles. The surface-to-surface gap is 1 micron, only 1 micron. Very close, and people had not done this before. People had looked at the system but not come this close. And that gave some pretty interesting, you know, started a story. Okay, this was still an equilibrium system, and of course fluctuation dissipation holds. And we studied the, you know, mutual cross correlations and all that. But most importantly, we found clear signatures of a resonance in the motion of the second particle because the first particle was driving it as a response. And you could actually tune the width of the resonance pretty fascinatingly. So in air, of course, you know that if your damping is lower, the resonance gets sharper. Here, this is a resonance driven by friction. And if you actually increase the friction, you get narrower widths. So that is quite fascinating, but there is interesting thing is that if you now want to tune the resonance peak frequency, that does not happen easily if you have a liquid with higher friction, with viscosity, right? So we use this as a very nice tool for doing 2-point macrorheology, because 2-point macrorheology essentially is measuring the viscosity of these solutions of liquids at very, very small length scales, and this is different from bulk rheology because bulk will give you an overall property. I mean, rheometers typically will give you bulk rheology, but actually if you try to do these, you know, at like micron length scales, and then try to verify with a rheometer, you probably can get different things because any kind of inhomogeneities, any density fluctuations will not be picked up by the rheometer, but it will just average all over the place, and this one will actually pick up. So we published this. We of course tried PRL, and the comments were essentially why this cannot be published as PRL is that this is not non-equilibrium, because these are still an equilibrium system. We've done a good job in terms of really studying and, you know, providing the groundwork of then going on to more interesting territories. And that was, and this second one, of course, to measure viscosity, we could measure at like very high accuracy and very, very large dynamic range of like, you know, of in terms of viscosity of solutions. So that started off this quest, and how we made this non-equilibrium was, of course, by the way, I forgot to talk, I had written my collaborators, so most of this non-equilibrium theoretical support has come from people at Nordita. Supriya Krishnamurthy and Srikant, her very, very talented, Srikant Manikandan, her extremely talented student who's now at Stanford doing his postdoc. And there is a third person who is one of the organizers here, Ornob Pal, whom we've started working with. And Ornob has a paper here, which is basically doing this. Only thing is, the difference that he has, that they looked at, is that this drive is no longer by a sine wave, but the center of the trap is now moved by noise. It is modulated by a correlated Ornstein-Uhlenbeck noise. And he published this in 2013, and we have taken it and we have done all kinds of nice things with it. This is now a completely non-equilibrium system. You have some kind of an effective temperature, and most interestingly, you have, this is lambda, is the variable which describes the trap center motion, and it is, the correlation is basically exponential. So that gives you a very different, handle. This is a handle to control the non-equilibriumness as well, which you can do by controlling this amplitude of A. And you also get an effective temperature, which is a tau 0, which I'm going to just talk about now. So how do you find signatures of non-equilibriumness? One big thing is that entropy is generated. So how do you measure this entropy? If for equilibrium systems, for long run, you do not have, if you average over long enough time, you do not get any entropy. Non-equilibrium you get, and the classic strategy for measuring that is by looking at the probability. If you take a time series, probability of, in the forward direction, divide that by the probability in the backward direction, and just take a log and all. This is the classic way of doing it. This has some issues because, first of all, generating this probability distribution function for complex systems, it is not easy. For example, as a complex system as a kinesin moto, or say this particle that is trapped near a flow of a bubble, it's not easy, right? The dynamics analytically doing is very tough, getting this thing. The other part is that you need very long time series. And if you are doing your work with an optical trap, you need to hold the particle for a very long time in an absolutely identical condition. The particle, the environment should not change. That is not simple at all, right? So this was like, this is a classical strategy. What I'm going to talk about now, and I've taken some liberty, some poetic license or scientifically poetic license or whatever I can say, is there a quantum-like way? And why I say quantum is that because this, of course, borrows directly from the very, very well-known uncertainty principle given by Mr. Heisenberg, Professor Heisenberg. This is a thermodynamic uncertainty principle, and very much like that very, very well-known uncertainty principle, this too sort of puts bounds on the entropy. And one big thing that it actually relies on is that if you have a non-equilibrium system, you have currents, probability currents, which tells you that in equilibrium, for example, this is PA is the probability of the particle of the state A, AC is the transition probability. The probability of going from A to C and C to A are the same, and the current is 0. Whereas for a non-equilibrium system, that is not the case. Forward and reverse paths are different. And the stronger the non-equilibriumness, the more will be the current, right? And that is exactly what is used. You find these currents. You essentially, then the total entropy is, of course, you relate these transition probabilities using this, very well known. And finally, the total entropy is the sum over all events, all paths. So essentially what it tells you, this uncertainty type relation, is if this is like a lower bound of entropy, and that depends on the mean of the current, the more the current is, and lower the variance is. That will give you a higher bound of the lower, so more entropy is generated, which basically says that there is more directionality in the problem, in the sense there are more currents, higher currents, and the fluctuations are lower. So if you want to have more precise measurements of fluctuation, the system better generate higher entropy. And then our friends Supriya and Srikant, they came up with this great scheme in 2015, where even if you do not solve the trajectory, the dynamics, by just using the trajectory itself, you can come up with an actual measure of this entropy, where they showed it for these known systems, that this method where you maximize J by a strategy and look at it at t tending to 0, put that as an asymptotic limit, you get the real entropy. The whole thing is, of course, maximizing this. And that is, again, I'm saying somewhat quantum-like, because what you do is you essentially, in a time series, you do a Stratonovich type of, this approach product. So you take this, you write this current as some kind of an expansion of basis functions for me. This is how I try to look at it, simple connections. And this science, you essentially are finding out these coefficients here and maximizing them. And these can be different bases. So you can take linear, you can take polynomial, you can take Gaussian, like what I've shown here. And you keep on doing an iteration technique where you see where the entropy is maximized. And once you do that, you use, and that you do by these either gradient descent or particle swarm techniques, Python basically, these different packages you have in Python. And then you can actually go, you keep on doing this till you find an upper bound, maximize, right? And that, of course, we took, so that paper that I showed you, that was theory. No experiments had been done, okay? So we were the first one to do the experiments to validate this. And that we again used Arnob's baby, that is this stochastic sliding parabola, as we call it, where you have this trap center modulated by an Ornstein-Uhlenbeck noise, correlate noise essentially. Now this is the thing that I would really spend some time on. This is the optical tweezer setup. So you have the trapping laser, you have a detection laser. And these experiments, especially when you do with two particles, is really tough because you have two different trapping lasers, you have two different detection lasers, and the reason that you do not use the trapping laser to detect is that you do not want the detection signal to change when you change the power of the trapping laser, right? Because if you want to have different trap stiffnesses, you change the trapping laser power. So that is something you keep fixed. We have another detection laser. And especially when you're having two particles very close to each other, you better make sure that no particle or no laser beam talks to each other. Neither trapping beam nor detection beams, because if they do, whatever you are measuring is going to be completely wrong. And remember, you're actually focusing these spots to 1 micron dia, and you're actually getting out information of particles which are moving over tens of nanometers or even less, and you're ensuring that the correlation exists, which is hydrodynamic purely. So the reason that this resonance happens is because there is hydrodynamic interaction. I did not go into details. But you are trying to find out signatures of only that. So you have to ensure that the detection beams don't overlap, nothing. So you use all a mixture of polarization and all that. But importantly, but here, of course, we have not gone to the two particle, territory, which we plan to do anyway. I'll talk about it at the end. So what you have is this this thing called an acousto-optic. In this community, it's known as deflector mostly. When we used to do, measure frequency of atomic transitions, we used to call these as AOMs, acousto-optic modulators, where you actually have these crystals, piezoelectric crystals, where you give these, this large frequencies, and they show this thing, something called a Raman-Nath effect, and you have a diffraction grating of refractive indices in that. This is like a phase grating. So if you can modulate that grating, and that gives you both frequency as well as beam shift. So in this community, of course, people use it only for beam shifting, acousto-optic deflectors they are called. So how do I actually change my trap center, that modulation by sine wave or noise or whatever, is by giving that same signal to this AOM. So this actually is like a grating, so it gives you a zero order and a first order, and the first order starts jittering, moving around in the way that you want to. Therefore, this beam basically, these are some beam shaping lenses, and then you have mirrors, you have a polarization beam splitter, which combines the detection laser with the trapping laser. And importantly, you have this dichroic, which actually, dichroic means it reflects one wavelength and transmits another wavelength. You have the detection laser reflected out. This is the second one. Part of it goes to the camera where you look at the particles. This part is crucial because this is finally the detection mechanism which is allowing me to detect with high signal to noise any kind of trajectory, which is even very, very small, fluctuations of nanometers and all that. This part is crucial. Okay, so how do you measure trajectories? Video imaging, because you just put a camera, you don't need to do all these difficult setups with this photodiodes and all that. Camera, the issue, however, is that when you want to, typically are, these normal cameras that this being used to film me, that is like real time 30 hertz. So if you want, if you're sampling only at 30 hertz, your Nyquist criteria is 15 hertz, which means that you will not be able to register motions at bandwidths more than the half of the camera bandwidth. So if you really want high stiffnesses, you typically go to, kilohertz level, and then getting a camera at kilohertz is very expensive. Now, the other way, which gives you much more bandwidth, but it is a pain to align, is using photodiodes, because they have much higher bandwidth. So remember, a normal photodiode just gives you a total intensity, just gives you a total power. It does not give you displacement. So if you want displacement, then you have to take an array of photodiodes, or you take something called quadrant detectors, where it's like the whole surface is made up of 4 different quadrants of a circle. These are different photodiodes, and the signals are all differently obtained. You take, you subtract or add, they typically subtract to find out displacements in the X or Y. The problem with those QPDs, as we say, call them, is that the bandwidths are typically not too high. Okay, gain bandwidth is not too high. Better than that is what we do. This is called this part, balance detection, and that actually uses 2 different fast photodiodes. These are easy to get. These are less expensive than QPDs as well. But that is, again, remember, the photodiodes will not give you any displacement, just total. So what we then use is this thing called an edge mirror. And very carefully, you have to ensure that the detection beam is cut partially by the edge mirror, hopefully by 50-50, and part of it is reflected to one photodiode and the other is to the other photodiode, the transmitted one. And then you take a difference. And you ensure that these deflections are out of phase. Because what you're doing by this balance detection is you're cutting off the common mode noise. If you put the same beam in 2, then you will do nothing. This is a real pain to align, because it's very, very small. We are all talking about extremely small dimensions here. And unless you get an out of phase signal, your thing will not work. So, but then it gives you gain bandwidth of like 1 gigahertz, very, very high. So you can really go to extremely high frequencies to measure. What we do, of course, 3 micron particles. Typically the trap stiffness we can vary, 10 to 20. We can probably go higher, but that we are limited at the moment by the laser power. And of course the scattering is a big issue. So what we do, this is very important. This is very important. This figure of our, confidently being able to measure displacements of even a nanometer at about 10 kilohertz, that came after 5 years probably. It's very tough, because you would suddenly have the line noise coming in, 50 hertz, and you completely go mad trying to find out where this comes from. Now, the very important thing is, remember, in photodiode you're measuring in voltage. So you have to somehow convert that into displacement. That is not simple, because you essentially are doing a conversion, and that conversion you do either by using the fact that the diffusion coefficient of your sample of water or something is known. Then you essentially measure the trajectory, you take the autocorrelation, you take in time domain, you can use the equipartition theorem, you do in frequency domain, you do like a classic Lorentzian analysis, and from there you get fit parameters, and you also get a noise equivalent power in terms of the corner frequency you get an amplitude, and that amplitude is directly related to the diffusion constant, and from that you can get a scaling. What we also do to verify is that we put known voltages to the AOM. We look at the video image. The video image, is calibrated by the software that the microscope company provides us, and that gives very good, that we have verified with the sizes of particles and all that, and it gives you some kind of a confidence check as to how your, this factor of sensitivity factor, that is your conversion of voltage to nanometer, works. Remember, every time you are changing anything in the sample, you're putting a different sample, putting different viscosity, different concentration of particles or whatever, this has to be redone. Because essentially, this is like a gradient force, it's a dipole force trap. Essentially, refractive index, anything changes, power changes, you have to do it again. So this is tedious. But this is very crucial, because otherwise we are not talking about displacements, we are talking about voltages. Very, very important. So of course what we then did is, this is again, as I said, the 2 variables is the displacement and the motion of the trap center. And this is, of course, a white noise. Both of these will always be there. This delta correlated white noise. You measure system trajectories. You see that if I give higher, and this is my temperature, ATR 0, this is an equivalent temperature, and you increase the amount of non-equilibriumness, you actually get a higher spread. The effective temperature is increasing, you get larger spreads. So what did we do then? So this was, again, I think given in Orno's paper, these ones. And then this is our check. So we use that inference scheme as I described for doing entropy. And from that, we actually use, so this is another thing. This is this stochastic force inference method, which has been given this 2020. I think it's a PRX paper, where actually you calculate entropy from information theory basis, saying that there is a rate at which you can finally transfer information from such systems if you want to measure them. So that gives very reliable measurements as well. So we actually used that also as a check, and these are the bounds from the theory, this red, and so from the SFI model, and we use different basis functions, linear and Gaussian, to find out the total entropy as a function of the noise amplitude, this A or theta, whatever you call it, right? And it is sort of not bad what we saw. So the interesting part, of course, then you can calculate the force fields. I'm not going into these derivations. Of course, you can find them done in the paper. You can see that the force fields that you generate by this is the method that we used. This is from the stochastic force inference, which is also, they match pretty well. So now we have sort of set up our test bed. It seems to work. Now comes to the new problem. And the new problem essentially is having a bubble, which, because there are, so remember this bubble we are creating by taking, the sample, how you do trapping in optical tweezers, you make a sample chamber, which is typically a sandwich to cover slips, glass cover slips, and you put a drop of solution, which a dispersion liquid with having these particles that you want to trap. Here for the bubble, what we do is we keep absorbing particles, okay, and some of them get absorbed at one of the cover slip surfaces, and then you come in with light, very, very strongly focused laser. Remember, the laser is focused using very high numerical aperture or very short focal length lenses, which gives you very tiny focal spots, so enormous intensity, going to like gigawatts per meter square level. And that, because you have absorbing particles, they heat up a lot, and they heat up to a level that they form a bubble. However, because I'm heating at that microscopic area, the whole water doesn't heat up. So the bubble is confined to only where the laser is focused. However, what is important is, if I see this is a 3D simulation, so this is my wall, this is the cover slip, you can say. The lower part of the bubble where the laser is intersecting is hotter than the upper part. As a result, the surface tension is lower in the lower part, higher in the upper part, because it's inversely correlated with temperature. And as a result, the lower part of the bubble wants to expand, the upper part wants to shrink. It creates some kind of force. This is called Marangoni flow. And because water is displaced near the bubble, more water comes in from outside, and you get continuous flows both axially and radially. Which means that this particle, when I trap it without a bubble, of course it is just a normal particle, and I use the trap center is modulated, but the moment I have a bubble, there are flows inwards. So which means that if I'll show you later, when you do a probability distribution, you can see, but of course this green is now the trajectory. You can see that it is more confined in the direction of the bubble. This is the direction of the bubble, right? Because now you have a continuous force there, a continuous sort of drag, the diffusion constant has changed, you can say. And because there is a continuous outward sort of a pull, the trap wants to pull it back. So the effective stiffness increases, as a result the displacement shrinks. This is in terms of, and you can see the force fields, green is the one with the bubble, red is without. Now, important is, this is a very difficult problem to solve analytically, because you need to model that, you put an analytical expression for that, that flow, and you probably need to solve the Navier-Stokes equation with unsteadiness and all, which is very tough. You measure trajectories, draw the current, do that maximization scheme, it is very much sort of possible to do. And importantly, this is the level we set for entropy that was without, entropy generated without the bubble. And what we see is that you expect, because there is more direction in the problem, entropy would reduce. And that is exactly what you see by the method, this our inference scheme, when you go closer to the bubble. As you come outer and outer, you actually see that as you go farther from the bubble, its effect reduces, and you tend to approach the situation with no bubble. And we try to sort of, again, Srikanth et al. Did the modeling part. So instead of, this is the classic equation without, this is the flow that comes with the bubble. Lambda, that is the trap center, doesn't change. However, there is the resultant, you know, the time scale does change for the bubble. Okay, 5 minutes only, my goodness. 5 plus 5, okay, so I'll really rush. So that changes the time constant, the diffusion constant both change, and we sort of use this A and B as fitting parameters, and you get, this is like, well, it does seem to asymptotically approach the no bubble case. So this gives us some confidence, and then this was the paper. Then the next things, I really need to hurry now. So again, these are just the results. I think I have set up some kind of a platform. So this skewness, so what is this? So, you know, fluctuations are crucial, and these fluctuation theorems, however, they set like some bound to the fluctuations. But what also is known that if you look at fluctuations, if you have any non-equilibrium phenomena, then the time that, you know, the time scales for which the fluctuations are above the average are actually, they were shown by Levy to obey some arc sine law. So at long time scales, they are more probable, something like that. Then, what is interesting that this is at when you're looking at very high time scales. You know that the time that this fluctuation the particle spends at above average is going to be dictated by a sine law, arc sine law. But what happens when you have finite time? So something called, and these are challenges to measure because these are not for long time scales. You cannot average so easily. These are transients. Reliable generic information is not easy. So basically, you define something called skewness, which is just, this is a classic definition of skewness, where you have these currents and, you know, their cumulants. So this is well known. But you can also see that for overdamped non-equilibrium processes, these scale as t. This is shown in these papers, and this scale is t square. So this tends to t to the power half for small t, which means this is 0 for, so delta S is like Gaussian level here. And for large t, this goes as this, minus half. And both at large t and small t, you see that skewness should go to 0. What happens, however, in the middle? So there is some, you know, possibility that you would actually get a finite skewness because you have 0 and 0 at both ends. And that is exactly what we saw. We essentially build up this current using some basis functions. We made some arbitrary currents with different choices of this C1, C2, C3, C4, and we saw that indeed there is finite skewness. And there is also a measurement time interval where actually that skewness maximizes. And we check that at lower t, upper t and lower t and all, they actually are proper. Okay, these are the results. So now what we actually use the entropy current. For particular values of C1, C2, C3, C4, we can actually get the entropy current. And that when we do, we actually see that, you know, look at T plus, this is maximum time, T plus is, you would expect at long T and short T that on the long run, these would be equal, 0.5 plus T plus, you should have equal times over the average and below the average. However, we see that as you increase the degree of non-equilibriumness by changing the amplitude of the noise, you actually see that you get more and more times that the particle spends below the average. And there is also a measurement time interval where that skewness maximizes. That actually maximizes. This is the highest skewness that you get, and that sort of is dependent on what is the sort of time interval that you're measuring. And this is the T max, that is the maximum, when what time you get the maximum entropy, that is also measured, that also changes. These are all verified by experiments. And we actually see very good match, pretty good sort of decent match. You can see that as you change the amplitude of the noise, you actually get these optimum times where the fluctuation, the current fluctuations will be below average. Most of the time it will be below average. So the takeaways are very interesting. Most interesting, I feel, is of course, the farther the particle is away from equilibrium, the more probability that you would find the fluctuations of the current to lie below average, below 0.5. And we also did it for, so this was a linear case, right? But then you can have situations where you have nonlinear cases. You can have bistable, you can have quartic. So if you go outside, Bishwajit has a poster explaining all this. So we actually saw that even in those cases, you do have this skewness finite. Discrete space systems, where like quantum jumps, where you do not have continuous currents. In discrete cases, what we saw, that it diverges at t tends to 0. That is not the same as, just Gaussian current. So then again, if you do shorter scale measurements, they still tend to lie below average. But this is what is really fascinating, that the nature of the fluctuations actually depend on the time that I'm measuring them, which is so much like what you have in quantum mechanics. But what is even more fascinating is that do our molecular motors actually optimize their time scales? Do they know? That is why we have so efficient machines inside us. Right, so then this was the paper, and just a continuation of that, I said that for long times we get arc-sine laws, and arc-sine laws are all over the place, like fluctuation of stock prices and dynamics and all kinds of things like that. They're very, very prevalent. Anything where you have stochasticity, you have arc-sine laws. Here what we have, the arc-sine law comes in the cumulative probability distribution. Again, for T max, for T plus, T la, this is the last time the time series change, and the maxima. These all obey arc-sine. So these are just a continuation of that. In fact, the previous work was born out of this. An MS student proposed this, and he looked at this, and then we suddenly, looked at the data carefully, and then we saw some very interesting stuff. What we saw there is that the more farther you move from equilibrium, converging to the arc-sine law takes longer time. So this is basically a deviation from the arc-sine law. And you see that as you go farther and farther from equilibrium, it takes more time for this to reduce. And this was again done for the stochastic, this is for the first law, this was the overall, this is theory, this is experiment. This was done for the bubble again, so this was the probability distribution I was talking about. So you see this is with the bubble, it becomes constrained, and you also get a skewness directly. So here as well, you see that the deviation is, so for the bubble, remember, reduces entropy. So actually the convergence is faster. So that also you check here. So that is basically, the end of the story. So this was the paper. And again, last year, so returning the roots again. So what am I talking about? I'm coming back to where I started from, this. But the difference is I drive one of them with OU noise. So it becomes non-equilibrium. The question is what happens to the other? Can I induce non-equilibrium by hydrodynamic interactions or whatever? Is that possible? Endless possibilities, because you can actually look at molecular motors, machines, engines which work like this, not been done before, viscoelastic medium. And so even you can make this problem in many ways. You can put this in viscoelastic medium, non-equilibrium, you can drive and see what happens. That's it. Thank you.
Thanks, Ayan. So we can take one or two questions.
The measurement with respect to the bubble problem, very fascinating. You actually have the other trapped particle which is kind of displaced as a function of this particular bubble.
It is basically moving towards the bubble. You see the probability, there's a skewness, right?
Yes.
So it tells you that the trap center has moved somewhat.
So in this particular case, you can pick up the fluctuations
of the particle.
Of the particle with what specific method? You
same thing. No, so that is like again, a two laser problem because you grow the bubble using one laser, and the particle is trapped using a second laser, and the detection thing is with that. So there it's a issue because if you come really close, then the drag force is so strong. I mean, it will just suck in. Then that's an issue. So.
Because the optothermal aspect would overtake the optical.
Absolutely, there are much stronger things. So those are very strong. But here also you crank up the laser power for your trapping laser and ensure that is. So initially it was interesting. So that's very details a bit. So if you are assuming they're in the same Z, if they are slightly up and down, so what Shubhra was saying, the student who did this, was that initially he was getting no sign of the bubble, which actually means he was sitting on some kind of a no-flow zone. And then, because that was not, so you leave the particle and nothing happens, then you know there's no flow. So you optimize that. So you lose a lot of particles in the process, right? You trap, you lose, you see how quickly it goes inside. When you know that it's happening well, then you do the measurement. So the thing is 100-second data, Pavan, for that long. So that is interesting.
Is that the trap still obeys
Yeah. That, there is now, the potential is effect. No, there is that is the whole issue, right? Because we do not have the analytical solution, but we do check the stiffness. It comes to be okay, but whether we can use that, because now it's an effective stiffness, so it's no longer optical gradient force. So there is an effective thing, of course.
Okay, so maybe we can continue later.
Yeah, I'm there in the whole day. So Vishwajit's poster, I didn't talk about that bistable and quartic and things at all. So all details are there. So please go, and I think people have looked at it. Flash talk as well he gave. So thank you, Dan. It was a pleasure.